In this question, I'm asking you to propose a synthesis of the following alkene molecule, starting from only alcohols of 2 carbons or less. Pretty much means you can use ethanol or methanol. They're your only carbon sources, which just means all of the carbons in this final product must have come from those alcohols of 2 carbons or less. You can use any other reagents necessary to complete this synthesis, but all carbons must come from those permitted alcohols. Right. So again, as usual, we're going to work backwards. And the first thing I'm looking at here is how many carbon-carbon bonds I have in this molecule here. It's a lot more than I'm permitted to start with, which is already has me thinking I'm probably going to use a Grignard or an organolithium to make some carbon-carbon bonds, which also has me thinking every time I use those organometallics, they're going to react with ketones and aldehydes or other structures, but typically they make alcohols, which means I'm going to try to work my way from this product to alcohols, because every time I can get back to an alcohol, that's a moment I can take this thing apart and start breaking it down to get it closer to those permitted starting materials. So let's just focus on the functional group that we see here. We have an alkene. Specifically, it's in its most internal position here, right? Well, how can we make alkenes? We know we can make them from E1. We know we can make them from E2. And in the lecture where you found this problem, you just learned another E1 reaction where you're taking alcohols and turning them into alkenes. And typically that's going to result in the most internal double bond. That was the reaction called a dehydration. I can still do this using good leaving groups like bromine and do an E2 reaction, but it's going to add more steps in there. So my thought is, why don't I just try to make this thing directly from a corresponding alcohol? Okay. Now, when I do that, I just need to put the hydroxyl group on this carbon or this carbon. No matter which way you do it, you'll be able to come up with a synthesis to make this molecule. So remember, there is no one answer when you're doing a synthesis question. So I'm going to go ahead and put that hydroxyl group on this carbon. So what I want to do is I want to draw that corresponding alcohol that I made this alkene from, which would be this alcohol right here. Now, the next step is, since I'm at an alcohol, this is where I can start to take this thing apart. And what I mean is, if this was the carbon oxygen double bond at one point, that means either this is a new bond, or this is a new bond, or this is a new bond. If you choose this one or this one, it'll take you the same route. But choosing this one will take you a different route. It doesn't matter which way you go here. Because again, there is no one answer to a synthesis question. So I'm just going to randomly choose. I'm going to choose this bond right here. I'm going to say this is my new bond. If I'm saying this is the new bond, this carbon right here must have been a methyl group. It's a methyl group, which means it was nucleophilic at this carbon. This is the carbon that came in and attacked this carbon to break the carbon-oxygen double bond. So what I mean is we're going to split this bond right here. So everything on this side must have been the Grignard, which must have been a 1 carbon Grignard reagent. So that's something like methyl magnesium bromide. Okay. Everything else here, all of this must have been a ketone, right? Because this is a tertiary alcohol. If we take a Grignard and react it with a ketone, it always makes a tertiary alcohol. So I just want to put this carbon oxygen double bond back and get rid of that hydrogen. So this must have been the ketone that we were using to do this reaction. Those two things reacted with each other, followed by an acidic workup to put this proton on the oxygen, but that formed that specific tertiary alcohol. All right, so let's focus on this ketone now. There's a lot more carbon-carbon bonds than we're allowed to start with, but we'll come back to that. We know we're just going to try to work this thing back to an alcohol so that we can take it apart again. But let's focus on the functional group that we see here. It's a ketone. I'm just asking myself, how can I make a ketone? Well, I know I can take the corresponding alcohol, which would be this structure here, and I can do an oxidation, either with PCC or Jones. I'm just going to choose the Jones method here. It doesn't matter if you chose PCC, it'll make the same ketone. Well, now I'm at an alcohol here. And since I'm at an alcohol and this thing has 5 carbons and I'm only allowed to start with a max of 2, this is a good time for me to take this apart. So I'm looking at this structure and I'm seeing a carbon-oxygen bond. This carbon-oxygen bond at one time must have been my carbon-oxygen double bond of an aldehyde, okay? Which means either this is the new bond or this is the new bond. And since this thing is symmetrical, it doesn't matter which one you choose. But the point is, let's just say that I'm saying this is the new bond. Everything to the right must have come from the Grignard reagent, and it must have specifically been nucleophilic at this carbon here. It came in and reduced this carbon-oxygen double bond. So everything on this side, including the oxygen, must have come from the aldehyde. So if we split that in half, I'll draw the left side first. The left side must have been a 3-carbon aldehyde. That specific aldehyde right there, plus everything on the left side, the 2-carbon chain, must have been a 2-carbon Grignard reagent, and I'm just randomly going to choose chlorine as my halogen here, but you could have chose bromine, you could have chose iodine. And then those two things reacted with each other, followed by an acidic workup to put the proton on the oxygen to make that alcohol. Remember, a Grignard aldehyde always makes some kind of secondary alcohol. All right, let's continue on with this aldehyde structure because it has more carbons than we're permitted to start with. Well, that just lets us know we got to take this thing apart again, right? So let's think about how we can do that. We got to get it back to an alcohol. Well, I'm just looking at this and saying, can I make this aldehyde directly from an alcohol? And I can. I can take the corresponding alcohol, which is this structure right here called 1-propanol. I can react that by doing an oxidation reaction to form the aldehyde that we have here. But what reagents can I use here? This is a primary alcohol. If I use the Jones method, I will end up making a carboxylic acid. That's not what I want. I have to do the PCC method here so that it stops at this aldehyde right here. All right, well, here I have propanol. I'm not allowed to start with a 3-carbon alcohol, so I got to take this thing apart again. Well, this is the carbon-oxygen bond. It must have been the carbon-oxygen double bond. That means this must have been the new bond. Okay, so this must have been a 1-carbon aldehyde, and this must have been a 2-carbon Grignard reagent. So let's split that in half. The left side must have been, again, and I'm just going to choose chlorine again, must have been this Grignard reagent plus the 1-carbon aldehyde, which is formaldehyde. All right, those two things reacted with each other, followed by an acidic workup to put that proton on the oxygen, and that formed that specific primary alcohol. And now I'm going to focus on this formaldehyde molecule because I'm not allowed to start with it. So I'm just going to ask myself, how can I make this formaldehyde molecule? Well, can I make it from an alcohol? Yes. I can start with the only 1-carbon alcohol, methanol. I can oxidize it using the PCC method because, again, if I use Jones, it makes a carboxylic acid. This PCC will make the aldehyde. That's what I want, so I have to be specific there. Right? And again, this is a permitted starting material, so I can stop there. But we got to come back to this structure here, which we also used here, but we don't have to explain it twice. We just want to explain how we made this Grignard reagent from the permitted starting material, which was an alcohol. All right, so how did we make a Grignard reagent? We used the corresponding haloalkane. So I put that chlorine back on that carbon. How did we make that transformation? We use magnesium metal in some sort of ether solvent. I'm just randomly choosing diethyl ether. All right, well, here we have an organohalide, which we are not permitted to start with. But I'm just asking myself, can I make this directly from the 2-carbon alcohol? The 2-carbon alcohol is ethanol, and that would be a permitted starting material. So how can I make this transformation? How can I turn ethanol into this organohalide? Well, there's a lot of ways you could do this. You can use HCl. It's a little sluggish. Or you can use SOCl2. Could use that. Or you can use PCl3. Any one of those would have been fine to make that transformation. That gets us to this permitted starting material. All right. One more thing we kind of want to explain in this one is we got to come back to this structure right here. This was methyl magnesium bromide. We haven't explained exactly how we made that yet. So let's do that because that carbon is in our final product. So if I want to make methyl magnesium bromide, how can I make it? Well, it's a Grignard reagent. And I know I can make a Grignard reagent from the corresponding haloalkane, which is bromomethane. And I know I can make that using magnesium metal in some sort of ether solvent to do that transformation. Then we just have to explain where we got this bromomethane from. Can I make it directly from the alcohol, the corresponding alcohol? Yes, I could do that with HBr or SOBr2 or PBr3. Any one of those will do that transformation. So here we have provided a synthetic route to that specific alkene using our permitted starting materials and the reactions that we've learned so far. And again, this is just one answer to a question like this.